Okay, hello everyone. Let's start today's session. I hope you had a great day so far. We are going to continue solving some examples today. So, first of all, we get more familiar with how we can drive the transformation from time domain to Laplace domain and finding the transfer function. But continuing the examples, we are going to also see how we can represent our transfer functions as like a block diagram. As you already know that the control system, theoretical representation of a control system are normally based on the block diagram. We are going to see how we should like deal with them, how we can simplify different type of uh, uh, block diagram to find the general transfer function out of the block of those block diagram and solve some example on that. Any question about the last session and what we discussed for like Laplace transform, S domain, time domain, transfer function? No? Okay. We still have two examples from the left off from the last session, so we are going to talk about them and then move on to the next set of example, which I already posted on Canvas, both of them, the examples and the solution. Now, the next example says we wanted to have the transfer function, okay? And, oh, yeah, we have the transfer function. We know the input. Now we wanted to see what's going to be the output, both in S domain and time domain, okay? The transfer function that we have, what is it? I think I am in a wrong. Uh, oh no, it's good. So we have a transfer function here. It's 1 over s squared plus 5s plus 6, and we consider input of our system as 1 over s, which is the step function. Okay. Now, when we wanted to like calculate the output, because we know that basically transfer function is, come on, work with me. Oh, come on. It's a little bit delay. The transfer function is V out over V in. Okay. Now, since we know that, basically it means that we have to like multiply the transfer function to the input so we can find the output. Okay. If you do the multiplication, okay, you would find that the output S domain formula equation would be 1 over s times s plus 2 times s plus 3, that these two terms are the expansion of the s squared, come on, s squared plus 5s plus 6. Okay, so this is a mathematical kind of like simple expansion of the second order to the roots of that second order equation. Okay. I assume you know how to do that, right? Okay, good. Now that we have the transfer function, we already know how we can separate those zeros in a denominator. So we can have them as three separate terms. We already solved the example. We know how to do that. We know how to find the coefficients. Okay. And when you have that term, using the linearity characteristics of the Laplace transform, okay, you can inverse the formula from S domain to time domain by inversing each terms and then adding them together in time domain. Okay, that was the linearity characteristic, one of the linearity characteristics of the Laplace transform. So you have this one. Okay, it's 1 over 6 over s. okay, which is basically 1 over 6 times the step function. We are gonna talk about the time from 0 to infinity. So step function is 1. So we have the time domain of the first term. Next term has a s plus 2 in a denominator, which already like a time shift. So uh, basically, it means that we have to multiply our general function, which is a coefficient over like p. We can consider a over p. Okay, p would be the parameter in S domain instead of s plus 2. Okay, so that one is still the step function times that a. So it's going to be 1 over 2 times the step function, but transferring that p to the s plus 2, which is the time shifted, we have to apply e to the power of minus 2t to our general time domain function. Are we good? Now, same goes for the next term. Okay, it's s plus 3, so we have e to the power of minus 3t times the general function of that term. Is that clear? So very simple. That's how you can find, if you have a transfer function, you can find the output from the input in both S domain and time domain. Now, let's do another example. We have the transfer function. Now we have the ramp, okay, as the input. Okay, the ramp function as the input. The Laplace of the ramp function is 1 over s squared. So if you wanted to like calculate the output, again, very simple. You multiply the transfer function to the input. Now you have the output. Again, we have a, a, a function, a higher degree, like a third degree function in our denominator. We have to separate the poles and basically change these into the separate terms. Okay, we have a repeated pole. We already said that if we have a repeated pole, we have to consider all the powers of that repeated pole. So if we have a s squared, we have to have the s in one of the term in denominator and then s squared in another term in denominator. Is that clear what I'm talking about? Okay. And the next pole, which is the 0 of the denominator, is going to be s plus 3. Now you know how to inverse the s domain function to the time domain. A over s is the a times step function, so it's going to be a. B over s squared is b times the ramp function, which is t, so it's going to be bt. Okay, and the c over s plus 3 squared is the c times the step function that has shift, which means we have to multiply it by e to the power of minus 3t. Is that clear? So very simple. Now, let's move on to the next example series that we have. If my computer works with me. Example 2, share. Come on. Now, the first 6 examples are the same as we talked about in the previous series of examples. So I don't talk about the what's happening when we wanted to like calculate the transfer function out of the circuit. Yeah. Okay. So in the first example, we have RC series. We already know how to calculate the transfer function for an circuit of RC in a series. Okay, we already done that, and we know the transfer function is 1 over RCS plus 1. Okay, now I want you to see how we can represent that as a block diagram. This case is very simple. We have our input. Come on. And we want our output. What's going to happen between them? How we can transfer input to the output? Multiplying by transfer function, right? So we are going to have our transfer function, and they call these centuries as information technology centuries. See? We have to multiply the transfer function to the input, so we have the output. So when you want to represent that into the block diagram, it's simply input times the block, which is the transfer function, and it would give you the output. Are we good? Next example will be RL in series. Still the same. We have the transfer function. We know how to find the transfer function. And what's happening, if you want to show it in a block diagram, is that we have the input. We multiply it by transfer function, and then we are going to have our output. What's happening? Yeah. Okay. Now, as we proceed, this is the same kind of like process. You know how to calculate the transfer function. The block diagram would be input times the transfer function equal to output. Are we clear? I want to move fast from this one so we get to do the actual like example that help us to actually deal with the more complicated transfer function. Example 7. We have a system with two blocks in series. What's happening? That means we have our input. One block is G1, which gives us our middle kind of like parameters or the first output of our system. Then that output become the input of the second block diagram. Are we good? So we have G2, and then we have the general output, the ultimate output of our system. Okay. So what we have here is we have our input, we have our first block diagram, which give us the inside input or like the first step input output. That output become the input of the second block diagram, which give us the final output of our system. Now, how we can simplify such a system? Very easy. The whole system, okay, I want to go step by step instead of just using the formula, okay, for that. Generally, we want to deal with that as one block. If we want to deal with that as one block, that means we want to have the ultimate h of s, okay, which is, okay, so let's see the output over input, okay? Now, what is the output over input? Let's call this one x1, the signal that we have, the state that we have here. The output is x1 times g2, correct? Over the input. What is the x1? x1 is the input times g1, okay? And we also have g2 here over input. Are we good? So what's happening? What is the general transfer function? It's become the multiplication of the two series block. Do you see how we reach to that formula? So if you have two blocks, each of them has their own transfer function, and you want to simplify that to one block, one transfer function, okay? Two block in series means you have to multiply them, and then you have the general transfer function of your system. Are we good? In this example is 5 over s plus 2, 2 over s plus 3. So the multiplication of them will become 10 over the s plus 2, s plus 3. Are we good? Is that clear? Now, what if we have two blocks in parallel? So we have G1, we have G2. They are in parallel and they give us the output. Okay? Now, you can either show this as simple connection, or sometimes you would see a circle here, okay, that gets the input and output. And inside that circle, okay, let me actually try to redraw that. And you have, inside the circle, you have polarity of each input. So basically here, these two are added together to give you the output of that circle. Okay? This is how you might see in the block diagram. Another kind of like type. Now, if this is G1 and this is G2, and we wanted to like find out the H of S, which is the output over input, okay, we know, let's call this one X1, this called X2. We know the output is X1 plus X2, correct? Now, what is X1 and X2? X1 is simply input times G1, correct? This is G1, this is G2, plus input, X2 is input times G2. So your transfer function, which is output over input, or H of S, become G1 plus G2. So if you have two parallel system in your whole kind of like a circuit or like general system, so you have two parallel subsystem actually in your system, okay, what happened is that you can represent the overall transfer function by simply adding the each subsystem transfer function to each other. Are we good? In this example, we have 1 over s plus 2, 2 over s plus 1 over s plus 1, 2 over s plus 2. So simply the general transfer function would be the summation of the two, which you can see here. Are we good? Let's move on to more complicated example. What if we have a feedback? Okay, what if we have a feedback in our system? What is the feedback? In reality, when you have a sensor, feedbacks gives you the current value of the output so you can work on it and see how far you are from the desired value. Makes sense? This is the feedback. This is a general specification of feedback regardless of what type of field of engineering you work. Okay? Now, when we wanted to like show the feedback, we have our transfer function, okay, that give us the relation between input and output. Okay? Generally, without the feedback, we have G as the relation between input and output. When you have a feedback, that means you are reading output and you send it to the input for correction. Are we good? So, you are reading the output and you are going to send it to the input for correction. In this case, we call the transfer function of the feedback what's happening between the output and input, which now if you see in the feedback, the transfer function actually show you it's reversed, the input versus the output. You know? Now, you have the feedback. Now, you can have the forward feedback, okay, or you can have the reverse feedback. Forward control feedback adds the output to the input as a feedback. The reverse one would subtract the output from the input, so you have the change, the error as the input of your transfer function. Does that make sense? Are we clear? So if we have negative feedback, meaning polarity of this one is positive, polarity of this one is negative. So what's happening here, let's say x1. X1 would be the input minus the feedback. Is that good? Are we clear on that? So this is the negative feedback. And the x1 is basically the difference or the error between the output and input. Does that make sense? Now, what is the output? What is the output here? If you wanted to like x1 times g of s, right? This is the output of this block diagram, right? This goes here, this goes here. Output is the output of that forward pass transfer function. Are we good? Is that clear? Any questions? No? So our output is going to be simply x1 times g. What was the x1? The input minus FB. FB is here. What is the FB? HS times output, right? So FB is HS times the output. Correct? So the x1 is input minus HS times output. Are we good so far? And this is equal to output. Are we good? So if you move the output in the same side and input into the other side of equation, you would have 1 plus h of s times output, correct, is equal to input. So what would be the ultimate transfer function? Let's call it T of S. What would be the ultimate transfer function? One thing is missing here. I missed something here. Let me see what is it? No, that's okay. This is somewhere in the here mistaking. So what's happening is the transfer function is 1 over this one. Okay. This output is G times what's happening? Let me check that. I think I make a mistake. I made a mistake here somewhere. X1 is input minus FB. FB is H output. Output is GX1. So it's going to be G uh, is going to be, here. G, I forgot this G. Okay, now it's working. Now it's working. Sorry. I forgot to put this G here. Okay. Now, what would be the transfer function? It would be G over 1 plus GHS. Are we good? Is that clear how we find that? Is that clear? Any question? So if we have a feedback, the overall transfer function would be the forward pass divided by 1 plus forward times feedback. Is that clear? The general transfer function would be the forward pass over 1 plus the forward times HS, which is the feedback. Now, that plus happened because here we have a subtraction. If we have a addition in our feedback, so in our feedback, input is getting added to the output times HS. This minus become plus, so this plus become minus, so this plus become minus. Does that make sense? Are we clear on that? Any question? Do you want me to repeat that? I don't know. Yeah? Okay. Let's use another color. Or let's erase these. What's happening? My problem is, yeah, it has a significant delay and it is quite annoying. Okay. So we have a feedback loop in our system, and we're talking about the negative feedback. This one is G, this one is H. This is our input, this is our output. Now, what is X1, which is the input of G? X1 is the input, okay? The input minus output times H. Are we good? Minus output times H. Is that clear so far? Now, the general transfer function, or T of S, is going to be output over input, correct? Are we good? So, what is the output here? Is X1 times G. Are we good on that? So, this is X1 times G. And we have our input in the denominator. What is the X1? X1. Also, the TS, X1 we have already here. The TS become, come on. That delay is really bothering me. G times input minus GH times output. Are we good? Over input. Are we clear? So, this one is GH times, yeah, there is. Yeah. This one is simply, if you separate them, is simply G, correct? This one is minus GH okay, times output over input. What was output over input? TS, correct? GH times TS. If you move this one to the other side, that means 1 plus GH times TS is going to be G, correct? So, if we have that, what is TS? G over 1 plus GH. Is that clear? Are we good on now? So, if we have a feedback, your general transfer function would be the transfer function of your forward pass, which is the G, divided by 1 plus GH. Now, we already said, if instead of negative, here we have positive, this would change. That means this would change. That means this would change. That means this one is changing to negative and this one is changing to negative. So if in your feedback, you are adding output and input together, instead of 1 plus GH in denominator, you have 1 minus GH in denominator. Is that clear? Can I move on to the next one? Now, next one says that if we have multiple forward pass, okay, transfer function. So what we have, when I say multiple series transfer function in forward pass, I mean we have G1 and G2 in our forward pass, okay, and we have a feedback plus a feedback, okay, which that feedback also have its own transfer function. Are we good? And our feedback is a subtraction here. Now, how we could G2, how we could solve or simplify that to find the general transfer function? Who can tell us? Actually, the answer is in the slide, but let me hear from you.
To multiply G1 and G2 together.
Yeah, you have to go step by step. So first thing first, we need to take care of these two. What's happening is that they are in series. We already know when they are in series, the equivalent of that would be G1 times G2. Okay? Now, if we have a feedback, the general transfer function is going to be the forward pass, which is G1 times G2. Here we called it G. Okay? Over 1 plus forward pass times feedback. The formula that we found in the previous example. So now what we have is the general one is G over 1 plus GH. G is G1 times G2. So for like this example, G1 is 2, G2 is 1 over S plus 3, and our feedback is a unity feedback, so the HS is 1. Okay? We simply replace them. It become 2 over S plus 3, which is the G1, G2, over 1 plus GH. H is 1, so doesn't change anything. 2 plus S plus 3. Now, you know how to simplify that. Are we good? So this is what happened if we have multiple subsystem in forward pass and a feedback. Any question?
Exam, are you going to give us like a reference paper that's these feedback? Like, or are we supposed to drive that on the exam? Like,
What do
the
you mean?
math that you did, or like, we go through the steps to get big G of S by doing the multiplication of those, and then you have like T of S equals G over that. But that seems pretty like generic for. But
It's always like that.
right. But are we going to have that as a reference on like a sheet for the exam?
You can have that in your note in the exam. Okay, but remember that this is the general rule. It doesn't matter what is the system is. If you have series of the block blocks, the overall is going to be multiplication of them.
Right.
Okay. If you have parallel, you should add them together. If you have feedback, it's going to be the forward pass over 1 plus minus based on the feedback.
Right.
Forward pass times feedback.
I was just making sure that we could have that written down.
Yeah.
Okay.
Yeah, it's going to be open book.
Okay.
Yeah, it's going to be open. The exams are going to be open book. So you can have them, but we already derived how we can find them. So if you forgot them, you already know how to find the overall transfer function by going a step by step, actually driving instead of using these formulas. Are we good? Any question? Now, let's talk about a more complex situation. Okay? This is an example of complex situation. It doesn't relate to these two. Okay? So, let's talk about it. In example 11, we have parallel feedback path. What that means? That means you have a forward pass. Okay? Are we good? Now, we have two feedbacks that they are in parallel. And they are going to be added together and then subtracted from the input. H1, H2. How we can simplify that? Add H1 and H2 so you have the overall feedback transfer function, and then use that formula that we find for the feedback, which means the general transfer function is going to be G over 1 plus GH. H will be the summation of the two parallel feedbacks. Make sense? So the general feedback transfer function is the summation of the two because they are parallel. Are we good? And then the whole system transfer function is a simple feedback because we already simplified this one to a one transfer function, is become G over 1 plus G H equivalent, which is the overall feedback transfer function. Are we good? And it's plus because we still have subtraction here. Any question? No? Now, example 2L is a more complicated situation. We have inner feedback and outer feedback. So we have two feedback that are not directly connected to each other. So neither the forward pass functions. Okay, this is actually very close to this one, but we don't have this one. Okay, so you have two forward paths, which they are not exactly in series, and you have two feedbacks, which they are not exactly in parallel. Okay, so what you have is that you have one forward pass that is going to be feedbacked from its input. Oh, sorry. Minus plus. Okay. And then another forward pass that is going to be feedback again from the general input. We call it nested feedback. We have an inner feedback and an outer feedback. How we can deal with that? Any idea? How we can simplify that to one block, one transfer function? We have one inner feedback, and the output of that feedback will become basically it would be multiplied by another forward pass and then feedback to the general input. So two feedback inside each other.
What happened to the one?
This one?
No, look on the diagram.
This one?
On that other feedback, I mean, the second feedback.
Oh, wait, no, you just want the.
Let's redraw that, okay? I want to be clear. We have G1, G2, okay? We have H1 and H2. Okay? H1 would feed back G1, okay? And H2 would feed back the whole system. Are we good? So we have inner feedback and outer feedback. Is that clear now? Any confusion about what's happening here as a nested feedback when we have inner feedback and outer feedback? Is that good? Okay, how we can deal with that? How we can simplify that? Go ahead.
By simplifying the inner feedback first, and then adding like with the
Go
adding
ahead.
the output of the inner feedback to G2, and then from there you can do another you could solve the outer feedback after combining the inner feedback in G2.
Yeah. So what's happening in step one, we have to get rid of this inner feedback. So you have to calculate the transfer function of the feedback. We already know that. It's going to be G1 over 1 plus G1 H1. Correct? Now, when you have this block, this is in series with G2. Multiply by G2. Correct? So now you have the general forward pass transfer function. Are we good? Now we have another feedback. Again, forward pass over 1 plus forward times feedback. Okay, so let's write it down. The T1, which is this block, is going to be G1 over 1 plus G1 H1. This is G, okay? Forget about my handwriting. Come on. Okay? Now, this is T2, the series of T1 and G2. T2 become G1, G2 over 1 plus G1 H1. Are we good? Now, the whole feedback, which is our general TS, would be the forward pass, which is this one. Okay? It's a little bit complicated, but we are gonna try to write down somewhere that we could. Hopefully this would work. The denominator is what? No. T2 is the equivalent of the whole system here. T1 is a block here. So when you have a T1, actually your block diagram become T1, G2, feedback by H2, and this is going to be your situation. Is that clear?
Yeah.
Okay.
I'm saying, so with the T2, why wouldn't it be T1 times T2?
No, T2 includes T1. T1 is inside T2. T2 is here. T2 is the equivalence of the series connection of T1 and G2. Is that clear? No. So we have T2, which is in our forward outer loop path. Okay. So it's G1, G2, 1 plus G1, H1. And what is going to be the denominator? 1 plus H2, G1, G2 over 1 plus G1, H1. Is that clear? This is H. Forward pass, feedback, forward pass. The denominator is 1 plus forward times feedback. Are we good? Any question? No? No. Let's say that we have GS and we have a step function as an input. What would be our output? We already know that. This is another example. I wanted to repeat what's happening before. Okay, so this is another example. So we know the output is going to be transfer function times input. When you have the transfer function times input, you know what is going to be the output. You know how to transfer the input to the time domain, the output to the time domain. Okay, but what I wanted to ask you here as an extra kind of a step is, can you find the differential equation that actually resulted in the transfer function? How we can do that? Very simple. Okay, we know our transfer function is for this example is phi over s plus 2. What that means? That means the output, which we call it y, over the input is going to be 5 over, this is 5, over s plus 2. So the output is going to be 5 over s plus 2 times rs. Correct? So if you take care of this denominator and put it in the left-hand side, s plus 2 times y of s is going to be 5 r of s. Are we good? What is s times y? You can expand this, right? It's going to be sy plus 2y equal to 5r. If you wanted to transfer this to the time domain, what you would have? What is sy in time domain? And you can remember that? What is sy in time domain? You have the y. What's happened to the y in time domain that the transfer function in s domain become s times y?
First derivative.
First derivative. So in time domain, this one is y dot. Okay? The first derivative. Plus, this is the simple y. Correct? So it's going to be 2y equal to the 5 input. So here, now you find the differential equation that drives your system in a time domain. Are we good? Now, let's think about that. Let's say this is like the input is a current and the output is a voltage. Okay? Let's say this is the current, this is the current, this is the voltage. If you replace that, okay, it's become V dot plus 5V equal to the 5I. 2V equals to the 5I. What type of circuit do you think it would be? In one hand, in one side of the equation, you have current. In another side, you have voltage. What is, let's say we move this current. I wanted to like make it easier for you. The current is V dot over 5 plus 2V. Focus on this term. What type of component, electrical component, connect the current to the differential of the first derivative of the voltage? Current to the differential of the, is going to be capacitor. Because the current as a capacitor is C dV over dt. Okay? So if the current of the capacitor is C dV over dt, that means we have a capacitor. What is the value of the capacitor here? Current, this I1 is C dV over dt. Okay? That V dot is dV over dt. What is the C? 1 over 5. So you have a capacitor with 1 over 5 farad. Are we good? Now, how about the second term? What components linearly connect voltage and current? Linearly, without any differential and integral. Resistor. So you have another resistor and they are adding together. So they are in series. Is that correct? Is that correct?
Well,
They are in parallel. So the currents are adding to each other, not the voltages. Are we good? So we have a parallel resistor. Okay. What is the amount of resistor? Again, what is the Ohm law? V over R is I, right? What is the resistor? In this term, the I2, what should be the value of the resistor so the current become 2V? When you know the relation between the voltage and current resistor is V over R is I. What should be the R so it become 2V? Come on, what is the value of R? What should I put at R so VR become 2V? One over two. Are we good? So we have half a ohm resistor. And this is the circuit that represents this transfer function. If we have current as input and voltage as output. Are we good? Is that clear how you can derive the differential equation from the transfer function and then considering electrical circuit, you can actually draw the circuit from the differential equation. Does that make sense? Any question, any confusion about that? No? Okay. What if we have a feedback? How we can find the output? We already know that the input times output, input times the transfer function, the general transfer function, will become the output. Are we good on that? Now, what is the general transfer function when we have a feedback in our system? It was forward pass over 1 plus GH, forward pass time feedback pass.
Yeah.
Our forward pass is 2 plus S1. Our feedback is unity, and our input is 1 over S. So our output become our input. Okay? Times 2 over S plus 1 over 1 plus 2 over S plus 1, GH. Are we good? Now, if you do the derivation over to simplify this crazy division, which is not that hard actually, okay? You can find the YS. You can find what would be the YS. And if you have the YS, you can find the time domain formula of YS. What would be the output in actually time domain? We already know how to do that. Is that clear? Is that clear? And we already talked about that. If you have the transfer function, again, you can develop the actual physical system, either like it could be mechanical system or electrical system. We like electrical system because we're electrical engineer. Okay, so you can actually develop and find out what was the circuit that resulted in this transfer function. We already covered that. Are we good? Next one. What if we have 16. It's not a multi-loop actually, it's a one loop. We have a feedback again, but our feedback already has a transfer function. It's not unity anymore. The feedback H of S is 2 over S plus 1, and the forward pass is 1 over S plus 2. Now, I want to have a little fun, okay? Let's look at this 2 over S plus 1, okay? Can we expand that block to see what was in detail happening inside that block? We can expand it to a feedback, right? Are we good on that? This is the shape should kind of like be clear. This is some sort of a transfer function that could represent an inner feedback. We know that the feedback is G over 1 plus GH. This is extra, correct? And if we consider that as a feedback, how we can, so this is 1 plus S. How we can find the inner block diagram of this feedback, general feedback block diagram. The inner feedback would have a G and an H. Are we good? What is G? If the formula is 2 over S plus 1, what is G? It's 2, correct? So this is 2. If this is 2, what is H? 1 over 2 what? S. S. This is GH. S is GH. Okay? If G is 2, H become S over 2. Correct? So here we have S over 2. I want you to kind of like see in reverse. Before we simplify the block diagram, now let's have fun and actually expand the block diagram. Is that clear how we did that? Same you can do with the forward pass too. Right? Now, this is S over 2. What kind of component could be? If the output is voltage, the input is current. So in that feedback is reverse. The input is voltage, the output is current. Are we clear? So let me be more clear. The feedback works on a voltage, gives you a current. So the current is that H times voltage, which is S V over 2. What component could we have as H here? Is make a derivative of the voltage. So in time domain, it's become V dot over 2. Are we good? So it's a capacitor with what? With 1 over 2 farad of a C. Does that make sense? Are we good? How we reach that point? Let me know if you have any question. I want to be crystal clear because eventually you have to run this kind of like analysis. I'm not meaning in the exam or homeworks. Okay, just it's out there after you graduated. This is what you have to do if you want to like theoretically analyze a system. This is what I said is this is our feedback. Okay. Let's expand that block diagram of that general feedback. The general feedback that we have, the general HS is 2 over S plus 1. We can expand it into a subsystem, inner subsystem. When you look at this, it yells out that the subsystem is a feedback. Are we good? So what was the formula of the feedback? If inside this block diagram, we have an inner feedback. The inside should have a forward pass and a feedback pass, which the formula for that is G over 1 plus GH. And this is the general formula. So it's going to be 2 over 1 plus S. Are we good? So the G is 2 and the GH is S. So you can find the G and you can find the H. And now you know what's exactly happening here inside that general feedback block diagram. And you can do the same for the forward pass. Are we good? Does that make sense? Okay. Did you have a question?
No, I got it.
Yeah, okay. Now, in this example, what we want is to find the output when we have a feedback. And it's very easy. You have the TS, which is forward pass over 1 plus forward times GH. This is the formula. This is your G in the general subsystem. This is your H in general subsystem. So you have the TS, and if you wanted to like have like a step response, you simply multiply it by that transfer function to the input, and you would have your output. Are we good?
Is there a difference between that example? Well, do you think this sort of thing could apply to an earlier example where we had the nested feedback loops? Or is this like just, or is this completely different?
Which part you are?
Like I was just saying, like the current example with, I guess like since we're saying that like we could take a look at like a feedback loop, right? G of S and H of S, and just assume that, or we could break down either G of S or H of S as like feedback loops in of itself, right? Wouldn't that be, is that similar to what we
It's the opposite of this example. In this example, we had the inner circuit, the inner subsystem. We wanted to simplify that to a one block transfer function. So we get rid of the inner subsystem, that inner feedback, and then we get rid of the outer feedback to find out the general transfer function, that TS.
So in that current
In the
example, it's
other
the same.
example, we went backward. We have the general feed transfer function. We want to see what's happening inside. We want to expand it instead of simplify it. We expand it.
Okay.
Is that clear?
Is there a purpose to expanding? Like, is it just to analyze like what's happening at G of S and H of S or not? Looking
When
at
you
outputs?
when you're dealing with an actual system, okay, there are a lot of like troubleshooting going on in your system. Okay, you want to find out where is the problem. Just simply have the transfer function of the general system would not help you.
It only tells you the results.
It would only tell you the overall view of the system. Now, you might want to like focus on each part of your system, each subsystem. Now, how you want to analyze if you only have the general transfer function and you don't know what's going on inside. You know what I'm saying?
Yeah.
Yeah.
This makes it it makes it so that you can look at the system in more detail and maybe look for like where like I don't know a problem could occur. Like,
Yes. Yes, and more detailed analysis on the system.
okay.
Okay. Are we good? Any question about that one? No? Okay, this is 16. Let's go to the 17. Oh, we already passed time. Okay. I want to start the state space on the next session. So I encourage you to go over the file that I put on the canvas. So you would go over the example 17 up until the example 20. Okay, we have 4 other examples. Okay, so go over that, and if you have any question, okay, regarding that, let me know. Especially, I believe that example 19 would be a little bit kind of like I need a little bit more explanation. I try to actually kind of record a video and uploaded that, okay? But if you wanted to like go over that earlier than me posting those videos, okay? Let me know. We can have an office hour or like explain it through the email, okay?
Which slide is it? Like which?
I put the two PDF, okay, in the chapter 1 module in chapter 2 module in our Canvas course. So we have the frequency domain module. Okay, if you look at the PDF, there is example 1 PDF and example 2 PDF. This one is example 2. The one in previous session is example 1. Are we good?